So now that we've finished our floor system, we'd have that complete across the entire structure. Whether, in this case, we are talking a floor system, so we either have a crawl space underneath of us or a basement, something of that nature. If we were building on slab, we would have immediately gone right to our wall construction. So that's where we're going to pick up now. So Scott, I noticed that this 2x4 is painted on both ends.
Yes, it is.
Why is that? Just for looks? Is it tell me something as a constructor?
You said in the last segment you were talking about standardization and how if we can buy standard sizes for different structural members in different situations, we can increase the speed in which we build. So what our lumber companies, the lumber yards, have done for us is we know that we have, through the ages we've built at 8-foot ceilings, 9-foot ceilings, sometimes 10 and 12 foot, and today we get big cathedral ceilings and whatnot. But for our, let's say our perimeter framing, this is called a pre-cut stud. And what the lumber yard has done for us is they have pre-cut this stud to be the exact distance between our wall plates that we would need. Typically, in the old days, we would buy an 8-foot stud for a 8-foot wall. But if we look at the anatomy of a wall, we see that there are bottom plates, top plates, double top plates. We have all these different elements, so that 8-foot dimension that we need for a stud starts to get reduced. And the lumber yard now will cut us 92 5/8 inch stud that we call a pre-cut stud. And what we can do is run our top plate, lay out our plates, and then we just start sticking the common studs in and we go to town. We don't have to cut the board from a 96 inch standard board down to the 92 5/8 that we would have had to cut every stud in the wall.
So that's can be thousands of cuts, plus we're wasting that much lumber on every stud. So the pre-cut is faster, more sustainable, right, and hopefully that assembly line starts moving along correctly.
See how this is a reoccurring theme with our materials?
So if I take my 92 5/8, you said that was an 8-foot pre-cut, and I add a single bottom plate and a double top plate, I know that a 2x4 is 1.5 inches thick. So if I go 1.5 inches, 1.5 inches, and 1.5 inches, that takes me to 4.5 inches.
Right.
So if I take 92 5/8 plus 4.5, that takes me to 96 5/8 plus the 1/2 inch, 97 1/8. I thought you said we were building an 8-foot wall.
What we've done is we've taken into account a couple different things with this dimension. Is that the finish height needs to be at 8 foot, or that's approximately the way we look at it. So what they've done with this 92 5/8 dimension is they've taken into account what? Flooring, your 1/2 inch 5/8 drywall on your ceiling, so that when we put all these finishes in, we have as close to the 8-foot dimension.
So we come back, when we add our floor and we add our lid to the room, it comes back towards that 96 inches or 8 foot.
Exactly.
Makes perfect sense. Okay, so that explains the coloring there. And I'm gonna, with a 9-foot pre-cut and a 10-foot pre-cut, those will also be painted on the ends a different color. So visually we can just look at our racks or stocks of lumber and know what we're gonna pick from to build.
Absolutely.
So that makes a lot of sense. Now, we have to do layout again. It's back to our friend layout. We're gonna show a 16-inch on center layout, just a quick, simple layout technique. So if I'm laying out my wall, I gotta think how they're gonna build the wall, whether it's out in the work surface or they build it up on the deck of the structure. We know we wanna be 16-inch on center. there's a lot of different layout techniques, and you think 16-inch on center ought to be 16-inch on center, go ahead and Google it, look on YouTube, and you'll see lots of different videos of how people do layout. So it all depends on where you were taught, when you were taught, but they're all gonna get you pretty close to the same spot. So when we're laying out a typical residential or light wood construction wall, we're gonna have our bottom plate and one top plate marked. That's enough to build the wall and stand the wall up. We'll get into when that second top plate is added, where in the sequence that second top plate is added, because it's actually added later on in the framing sequence. So if I have my lumber here and we're using these as a top and bottom plate, I want to even them up or flush them up at the ends. We've already sided them to try to make sure that they're not bowed, twisted, warped, those kind of things. The most basic way is I can hook my tape on and I can start marking my 16-inch on center right on the 16-inch mark. When I do that, I can pull out my speed square, go right through my caret or my mark, and place my X where I want the stud to go. That way when I take my tape measure and I lift it up, and of course we'd have one here at the end, we always start and stop a wall with a stud. We'd slide over 3/4 of an inch because that is my 1/2 inch and a half, and that puts my 16-inch right on center of each additional stud that I've added to the wall. I like to use the mark on the side. You'll see techniques where they actually mark the middle of the stud, because when I build the wall, we pull these two top plates together, and if we're using the 8-foot pre-cut, we pull the top and bottom plate apart, we drop in the 8-foot pre-cut, and now the wall is exposed to go ahead and add our fasteners from top and bottom. We do that all the way through the sequence, tilt the wall up, and we're ready to slide it into place. Again, lots of different techniques. You'll see people push the tape out past the, if this was an exterior wall, push it out past the end of the board, the thickness of whatever our wall sheathing is. You'll see people mark the 16, back up 3/4 of an inch. There's a lot of different ways to do it. So as long as there's consistency, we usually land on the correct mark.
That's right.
Now, all we're talking about right now, Scott, is studs. Common studs, right? They're, in this case, we're building an 8-foot wall, so we have 8-foot pre-cuts.
Well, what do we call the structural members, say, around a door? Because we do, when we have openings in the house, we have special situations that we have to address, right?
Right.
Different structural components we have to add so that the structure stays up.
Yeah, we don't build boxes. We have windows, doors.
Right.
We have point loads coming down on different parts of the structure that we have to account for weight.
Here, I'll get
Let's
this
go ahead and move those out, and we'll move on into the building and talk about some of our components. Here we are inside of our 8-foot by 24-foot structure that we build in the lab to give the students the hands-on experience of light wood construction. You can see that we've got our perimeter walls built. Here we took the end of the building off, so this was actually an interior wall coming across here with a door opening. And then we'll discuss our window openings and an exterior door opening in a later video. So we can see that we've done 16-inch on center layout, and that creates common studs. So those are the studs that are following the 16-inch on center layout. That would be there to help hold up the wall sheathing, the structure of the wall, drywall on the inside, things like that. But we have these other components that we have to be worried about. And Scott there, he's showing our 16-inch on center.
So if I hook the edge of this stud, it carries across the entire wall that I would be hitting 16 on that same side all the way through. So that's just an illustration. You can see the outside sheeting attached already. But that's why we maintained this layout, is for our exterior sheeting as well as what we're going to put up on the inside, which is a JIT product, drywall.
And I noticed, Scott, when you put your tape up, we're hitting 16, 16, and here we're a little bit off sequence, and then we've got another stud right to it. It looks like there was some kind of splice right here. So this is one of those learn by doing examples. We let the students read the blueprint. They saw they had a 24-foot wall along the outside. We didn't have lumber long enough to build that long, and we didn't have 24-foot top plate and bottom plates, so they built the wall in sections. And that is 100% correct to do. We can build the wall in sections and then hook those sections together. The critical mistake that they made, though, was they pulled each wall section as its own 16-inch on center, rather than build the first one and then continue to lay out your plates based on the first wall section 16-inch on center. That way it carries all the way through the full 24-foot. That's why all of a sudden we get where this sequence starts to break off and we're not on our truly 16-inch on center anymore.
The way I was taught to lay that out when I was a carpenter's apprentice was I actually laid the plates linearly through the entire length of the structure. So if we were doing an exterior wall like this, it would have been the whole 24 foot of plates would have been laid strung out, all cut perfectly to length. And then I would have pulled from one corner all the way across the house with one tape measure, putting my marks in as I came down the wall. That was the way I did it because exactly of that happening, to where we screw the layup out from one panel to the next. Because it's not that huge of a mistake with regard to what you have to do to make it right. We just have to cut sheet goods. But the thing is if it takes me 15 minutes away from my task to cut one sheet of plywood down to fit my framing, what if I did that 20 times through the building, see? Then I just spent 5 hours. Now 5 hours at a $60 labor cost, you start to see how these tiny little mistakes in layout can just dog your job all the way through. It takes that beautiful black line, starts putting it in the red.
Yeah, and by black we mean profit. Red we mean loss. And so not only did you lose time, we lost product.
Oh, absolutely.
We've paid for a full sheet and they have to trim off 6 inches. That 6 inches gets thrown in the dumpster, right, and that's money being thrown away.
That's right. Whereas you had 4, 5, 6 inch rips and now you need 30 inches. Now you got to go to the lumber yard to buy that final sheet that you just cut off every other.
Right. Depending on the spec, we may be running our sheets of drywall this way. We may be running our sheets of drywall up and down. So if we don't hit 16 inches on center and that sheet falls out in between two studs, the end of the sheet doesn't have anything to bear on. So we either trim the sheet back to the next closest stud, or we take time to add in another stud. Maybe when you go in to add that extra stud, there's already been plumbing run through the wall, wiring run through the wall. It can just be a disaster. Follow the layout, because all of our other products are based on that layout. So here we've made mistakes, but that's how we're learning. And they go through their sequence. You can see we built the wall in multiple sections. Now, when we get around a window or a door, we start to get this mass of lumber, a lot of extra lumber that's put into place. And these now start to have specific names. So the crew, in case they're doing any pre-assembly where the team's working on layout, another crew member is crowning all of the studs, we may have yet another member who's pre-building window and door headers, corners, or marking out king studs, jacks, and items like that. So in this wall, Scott, where are my king studs and what is their purpose?
Okay, so a king stud rides along, it defines your doors or windows. So you can see right here we have a stud that runs from bottom plate to the top plate. So this stud that my hand is on running down is the king stud on this side. The king stud runs the full height of the wall like a common stud. So really a king stud is just a common stud that is one of the structural members on the side of a rough opening of a door. So we have a king stud on either side, here and here. Now the inside stud is a little bit different bird, because as you can see, it's been taken off of the bottom plate, but it stops here underneath this structural member that defines the top of the door head. This is called a trimmer or a jack stud. And guys, once again, I'd like to reiterate to you that Mark and I use a lot of different terms. Nomenclature is regional, sometimes city to city, area to area. Inside your textbook, you're going to be given a set of names for all of these structural members. That's what you'll be responsible for on the tests. But when we speak here doing these little snippets for you guys, we'll use a lot of different language because when you get out in industry, this may be a jack and you might be tested as a trimmer. But they're both right. Okay, you just have to be right on the test. So remember what the book says trumps it all.
And don't just learn the material to regurgitate it on the test. It doesn't make any difference after the test, whether it's a jack or a trimmer. You just have to know what its function is. In this case, the jack and trimmer help support the ends of the header. In this case, this is just a little miniature header. The header is there to take load from above. We'll get into that as we work through our framing sequence. But our king stud caps off the ends of the header. The jack or trimmer helps hold the header up.
That's where your point load is on the head.
Right. And depending on the specs, Scott, can we have more than just these two underneath the header?
Absolutely. As we get above 6 foot openings, and I'm going to say as a standard in residential, you'll put another trimmer in. Sometimes even more, depending on how long the span is.
Right, and the engineer may call that out. They may say, hey, under the end of this engineered header, we want a buildup of 4 jacks or 4 trimmers. Right. If that's what they call for, we take the rough opening of our opening, let's say it's 6 foot. We know the header is going to run past the rough opening here, just like it does here. The header runs past the rough opening. Then we have to see how many jacks or trimmers are stacked up, and that will give us our header length.
Absolutely. So, to reiterate, we've given you a lot of information there. King studs, trimmers, or jacks. The king stud, plate to plate, we nail the trimmer into the king stud. That's what keeps it laterally from shifting. Then we put our head in, or a header. As Mark said, in this opening, this is a nominal header. It's what we can do for all heads that aren't in bearing walls, right?
Correct.
So a 3.5 inch tall head is perfectly fine because we're not going to support any loading from the floor above or the roof in this wall. Unlike what we would do in our exterior walls. And if you come into the structure, you can see that now we have a much larger structural unit in the wall as a header.
Yeah, we've added to our height of the header, which makes it stronger.
And how it carries. Because if you look here, as this joist or rafter here, our roof is bringing load down to our exterior walls along the eave. So this head, right, takes that load, shifts it out, and brings it down the king stud and the trimmer.
So if I understand you right, Scott, if we didn't have this header and this system up above the wall is providing weight, would it just start slowly pushing that down?
Absolutely.
So this
might
serves as
damage
part
our window. You know, we could be damaging outside siding, trim pieces.
Masonry.
So the whole thing's going to go to hell in a handbasket. And once we get deflection, what are we going to get in there?
cracking.
Cracking, and cracking means what?
We're coming back and working on our job and spending money that we didn't budget for.
That's right.
So if we watch that load, it would come down through our plates, comes down through our blocks, and as the load gets into the header, it transfers back over into the king and jack or trimmer down below and pushes the load out around our opening in the wall.
That's right. So the greater the load is from the second floor and the roofing, the bigger that structural member or that header is going to become. Sometimes you'll see 2x12s. Sometimes they're so big we got to go get LVL. We got to go get structural or engineered lumber and use for heads.
Yeah, depending on the span and the spec, we might be putting in a big piece of steel to span
Exactly.
12,
Exactly.
16, 18 feet to open the opening up to have a big door or window
How
underneath
big is that
it.
head behind you, the backside of your house? It's all glass.
Those are 14-inch LVLs, and every so many feet based on the specification, we built a 16-inch wall to take some of the load off of those beams. So, and the LVLs can be stacked up side by side to make them stronger. So those are other things, again, that we're always going back to the plans and specs. What did the engineer say is going to work here? Doesn't mean that we take it as gospel. We have to read through it and understand it. But if I have a question on the plans and specs, and I've been taught the nomenclature or the terminology, I can have an intelligent conversation with that engineer and say, hey, on plan, A or page A4 in the architectural drawings, I've got a question on the west wall, wall section, and talk about that based on the blueprint, and then say, now, specifically, the header calls out this height by this length with this much bearing on each end. I've got a concern or I need a clarification. But at least if you're the engineer and I'm the field superintendent or construction manager, we can talk the same language and make sure we're talking about the same component in the correct wall and that I get my question answered so I can build the building correctly.
Right. So with windows, we have a little different situation than we do with doors. And I'll move these horses out of the way.
Sure.
And why don't we talk about cripples in here, what those are above the header, and then what we
Down
do
below. Sure. So again, on our blueprint, we're going to have our window openings, and it's going to give us what they call an RO, or a rough opening. The RO is simply a function of the size of the window, the width and the height of the window, plus a margin of space, because we can't have the RO, the rough opening, match the window perfectly. We know that the lumber's not going to be perfectly straight. When it came from the manufacturer, the window may have a slight 1/16 of an inch bow to it. If we had this perfectly tight, we wouldn't be able to slide our window in. So the rough opening is always bigger than the window of the door. It allows us to slide the unit in, then shim it and adjust it. Again, we're always making corrections, plumb, level, and square. So it allows us to do that. So the rough opening size would come off the print, but you can see we needed some structure in the wall underneath the window. So this is where we get into our window sill, and then we can get into the pieces of lumber down below. Now remember, some of these might look like they're randomly placed in the wall. Some of our blocks below the window are our 16-inch on center. If we look here, this right here is 16 inches on center. But we've added these secondary pieces that are under the ends of the windowsill to keep the windowsill structurally sound and level. These pieces, cripples, is a common term that you'll see in the industry on a blueprint.
The cripples are in there to carry the sheet good past the opening. So they're always found on your 16-inch, 2-foot, 19.2 inch, whatever your center layout is, these cripples will always lay on those.
So that would explain why we have a layout like this then, because it looks funny to someone not in construction that would come in and say, why do they have a block here and then this? Why wouldn't you just remove one of these? Why wouldn't you have just filled it in? It all goes back to our 16-inch on center layout. That was pulled all the way through. Then after the 16-inch layout, 16-inch on center layout was placed, then we would place our rough opening, which shows us where the king stud and the jack of the trimmer goes. And then we know our header, and above that, we'd still have our 16-inch on center, plus any blocking that was necessary to strengthen the header. So we'd automatically see the continuation of that jack or trimmer above the header, here and here. We'd see our blocks, our cripples running through at 16 inches on center up above, so we can continue our sheet goods, drywall on the inside in this case, and OSB structural sheathing on the outside. So that's why the spacing looks a little off. It's because we've broken the common stud layout with a window and door opening.
Right. So the way I would have laid that out myself I would have laid, like if we were doing this wall all the way down, I would have had the full 24 foot of plates laid out. I would have pulled from the end. We always start from one side of the building, okay, not to get confused. And then I would have laid my common stud layout all the way through it. And then I would have calculated, using our blueprints, where all the center locations of my windows and doors along that wall, where my partitions are, where my leads are, so really what I'm doing is I get my common layout and then I just do all the openings. And that way I know where all my cripples are because I've laid it out with the common layout.
So that blueprint's going to tell you the center line of the
Sometimes.
window? And will
Definitely.
it also show me the height in the wall that it goes to?
Sometimes, yes.
Okay.
But you would know more about that, what industry practices are. To me, when I was doing things, if I knew that what my rough opening, if we have a standard door, I always know that it's going to be, however wide by 6'8".
Right, because we're pulling the door openings from the floor system.
Right.
On our windows and doors,
Or not.
they might, or not, depending on the layout. Our windows and doors, they may give us a sill height.
Yeah.
They may give us a
Right.
header height. And then we know everywhere through that structure, our header is going to be set at the same height, and then we know our rough opening will drop down from that header. That gives us that continuity
Right,
on
the
the
head.
outside,
Yeah.
so all the windows are lined up, everything looks visually pleasing.
That's where I was going with it, was that this head height for our doors would typically, at least in my mind, dictate. But that's not always the case, right? I mean, your house, you have very high ceilings.
Yeah.
And your door and your windows may be at different heights just because of the nature of your house.
Well, and based on architecture, right?
Right,
Certain
yeah,
types
absolutely.
of architecture, we look at modern Prairie, from the Prairie style, Frank Lloyd Wright. He liked to use small windows as far as width-wise, but very tall vertical windows, but then also alternate those with little cube-style windows.
Right.
So your header height could be jumping all over the place in the wall. So you'll have to pick that up from the blueprint, or you ask for clarification.
And I live in a little ranch, and all of mine is even
Yeah,
around.
all the
Just
way.
a typical, like this structure, everything would line up at the head.
Sure, sure. So have we covered all the pieces in the wall, or are there additional framing pieces that we'd have to worry
there are
about?
some additional framing that we need to look at in different situations. Mark, why don't you go ahead and tell them about why we use a top plate?
So we talked
Or
earlier.
a double top plate, rather.
right.
Double top plate.
We talked earlier that when we build our wall, we do our layout. We do it first with the bottom plate and a single top plate. Once all of our walls are stood and we've plumb, level, and square the walls, because these walls have got a lot of movement to them. Until we put in all the final pieces, you can see the walls will still move. We haven't attached all of our structure above, nor have we blocked and braced everything. So we'd want to plumb, level, and square our walls. Once we've done that, it's time to lace in, is a common term, your second top plate. And that helps tie in our interior walls to our exterior walls. So every time those two walls tee in together, if we had put in both top plates as we built the wall in the ground, we'd have a joint. And we have a perfect example right here where that was done, and it was done incorrectly. So when you look at our double top plate up in the corner, you can see the interior wall, both of the top plates stop before they reach the exterior wall. To truly make the structure sound, we would have wanted to take the second top plate here and lace it or lay it in to the outside of the exterior wall, and that would have given us this situation where the top plates lay in like this. And that really locks in. Now my exterior wall has a harder time leaning to the outside because it's got the resistance of the interior wall second top plate.
So a good illustration is right here, where we have two wall panels coming together. Instead of breaking the top plate, on the splice, if they had done that, then it would have allowed that to hinge. We could sit right here, push on this wall, and it would have done this. But by running the double top plate, you can see that the second top plate spans over where the two wall panels come together. That greatly increases the strength of the lateral run of the wall.
So that's very similar to when we were talking about where we stagger the joints in our subfloor, or you stagger the joints in a CMU wall. It's to strengthen it. So we'd want to stagger the joint in the first top plate to the second top plate, just to build that strength of the system.
Absolutely.
So I'm going to grab some wall corners, because that's another critical component of our structure. So another reason to have a double top plate, you say, well, it's an extra piece of lumber. There are multiple framing techniques depending on where you are in the country, where you are in the world, again, code book, things like that. It may be a sustainability issue. You want to use less lumber in the house. When we do a double top plate, we said we were 16 inches on center as a common wall framing. Roof trusses, however, may be laid at 24 inches on center. So when we think about that, I've got a stud here. I had a stud 16 inches back. That truss that's going to build up the roof of my structure was at 24 inches on center. If I pull over 24, I'm landing somewhere right here. If I had a single top plate, that single 2x4 does not have enough load capacity to hold the weight of the roof. When we talk about live load, which would be snow load in a lot of cases, wind load, and the dead load, the weight of the roof system itself, it would actually cup that single top plate down and it would start to sag and cause damage. When we run a double top plate, it's now strong enough that no matter where that truss falls, regardless of our layout down here, we can support the roof. There is a process called inline framing where we would actually run our studs perfectly in line with the floor system down below the stud and the roof truss up above. That way we take the load from the truss to the stud to the floor system to the foundation. So you'd have to follow your layout. Maybe that's a 19.2, maybe it's a 24-inch on center layout. It's a very sustainable way to frame because we get to use less material. So the question is, why do we not use it? It's practice. We don't have enough practice doing it. Most of our crews are used to 16-inch on center layout. They can go very quickly, very rapidly. When you do inline framing, you have to go a little slower to make sure every member stacks on top of every other member, because if you don't, we have failure. So multiple reasons why we use a double top plate.
Absolutely. Okay, so why don't we take a look at how we would frame up corners.
Sure.
Because we have different corners that we can use, different configurations for the 2x4s and insulation and all these things.
Right. Very rarely do we build a round building. You see it every once in a while, but we deal with corners a lot. So there's multiple ways to build corners. That's, I guess, the nice thing about construction, and really in a lot of the codes, there's a little bit of gray area written into the code book. If it's a life safety issue, you're not going to have a lot of variance. But in other situations, there's some gray area so that you can meet the needs of the job, but still build a good project. So you look into the code book, and if we're talking about corner construction. So in this case, we'd be talking about the four corners of our building.
Where do you want to start out? Can we start with the California? Is that the California?
Well, let's start with the oldest corner, right? Probably the most traditional corner. This is just a strong corner or a solid corner. So imagine this wall. You can see I've got a bottom plate here and a bottom plate here. And this is the outside corner of my building. I'm coming around and changing directions on my structure. So we'd want to run our 16-inch on center layout going that way and coming towards me. But we have to build up the corner because we need to catch sheet goods on the outside of the building this way and this way, and then when you picture the inside of the building, we'd want to catch our drywall. So if I tip the wall up to you, and now we've got a bird's eye view down at the top of our wall, this stud right here catches this sheet of drywall that comes along the inside of the wall. This stud here catches the sheet that would come off this other wall, and they both have a place to stop and be attached. So this is a traditional corner, a strong corner. It may be spec'd because we have to hold up some additional weight there. It may just be being done because it's fast, it's quick, it's easy. The crew doesn't have to think. They just stack up 3 studs on one wall, the 1 stud on the other wall, and go. It does affect your layout, because if we'd hook our tape measure here, you've got to understand where your 16-inch on center hits in relationship to pulling both directions. So that's one way to build a corner. Finally,
So what's the biggest con? Definitely it's the strongest corner.
right. So the biggest con here is insulation, right? We know we have to insulate our structures, right? That's, when we're outside in cold weather, what do? We put on more clothing. That's insulation. What we're trying to do is break that thermal path between hot or cold air and ourselves. We do the same thing with our wall structures. We're trying to have a thermal barrier of some sort between the hot or cold of the outside and our conditioned space on the inside. So the problem with a strong corner or a 4-stud corner is we have no room for insulation. So when we think about building science, everywhere that we have a piece of lumber, we cannot put a piece of insulation. So everywhere we have a common, a king, a jack, a cripple, a header, a corner, any of those pieces means we cannot have a piece of insulation. And you say, well, Mark, it's only 1.5 inches. How bad can that be? But when we count up all of those pieces of lumber in a wall, and we take that over the course of a whole building, what it equates to is roughly 1/4 of the building is uninsulated. And by that I mean it has a piece of lumber, so it has no insulation. And if we didn't do any exterior insulation, that piece of lumber becomes the thermal bridge that energy can move through. If I've got cold air inside and warm air outside, it wants to travel through the stud with a bridging effect, or flip it in the wintertime if we're in an environment where we have to heat the inside of the house and it's really cold outside. That's the bridge that leads to thermal transfer. We got to remember that hot moves to cold and wet moves to dry. So in building science, we don't have to have an advanced degree. We need to remember those 2 things. Hot moves to cold, wet moves to dry. That helps us build a better structure. So when we have a strong corner or a 4-stud corner, you can see I have this mass of lumber that I can't put any insulation in my wall, so this corner is always going to be hotter or colder than the rest of my wall, depending on exterior temperature, interior temperature. So a way around that came the California corner, because that's where the technique was first used. Somebody started looking at the corner and say, I need to get some insulation in there somehow. So again, we have bottom plate and bottom plate representing the outside corner of the building, my 2 walls coming together. And in this case, they did a 3-stud corner. So you can see we had stud here, and we changed the orientation of the studs. This allows for the interior piece of drywall to catch right here, this piece of drywall or interior finish, whatever it is, to catch right here going this way. I can break my sheet good here on the outside. My sheet good can break right here on this corner, but you can see we've left this void right here. So when I'm inside the structure and it's now time to insulate, I can actually tuck my insulation in behind this stud and at least get some kind of R value, that's the thermal resistance value, to the transfer right through here. And at least now I've insulated part of my wall, as opposed to this where I can't put any insulation whatsoever. So this was kind of the first technique. This is now becoming very common in practice, to be able to tuck that piece of insulation back in there. There's an even more advanced step that people can go to, but like all designs, there are some flaws as well. So the last one we're going to show you today is a 2-stud. So you can see we went from a 4-stud corner to a 3-stud corner. Now we'll talk about the 2-stud corner. Bottom plate, and now we've only used 2 studs. So we talk about the outside of the structure. We have our OSB coming down the wall or our structural sheathing, it's got a place to stop and be attached. This sheet comes along the outside of the wall. It's got a place to stop and be attached. Our drywall comes along the inside here. It's got a place to be attached. And look at this, we've got this full cavity. So when the wall is built and I'm inside, I can reach all the way in and tuck in a full depth. That 3.5 inches can accept a full 3.5 inches of insulation. And now I've really insulated my wall much better than the 4-stud corner, better than the 3-stud corner. So this is awesome.
But wait, Mark. What takes care of the drywall coming in from this direction? There's no stud here any longer.
I missed that one. So our OSB comes here and here, we're good. Our drywall comes this way, it's good. Now our drywall sheet comes and we have nothing to hook it to. So it's gonna move, which is gonna crack in the corner and cause a problem. But they did develop a product called a drywall clip. And that's a metal clip that attaches to this stud that you put periodic spaced along the stud, and that metal clip keeps the drywall from getting collapsed into our cavity. The issue is our drywall crews don't love them, because if they don't get put on perfectly straight, we can get a wavy corner, which then means our owner or our architect comes through and writes it up on the punch list and we're trying to fix the corner. So again, if we're trying to go with some kind of super insulated house, we may look at this technique just to get as much insulation in the wall as possible, but it comes with an extra labor step that has to be done. So right now, I'd say the most common corner we will see is our 3-stud corner. You will still see some strong corners based on load-bearing capacity and things like that. And then this one is probably what you'll see the least amount right now, just because of those added steps that need to go in, and the potential, not always, but the potential for a wavy corner or non-straight corner. So let's spend a moment talking about dimensional lumber. And by that, I mean lumber that has been sized for us in the field. We have increments that we work with. I'm holding a standard 2x4. Now, it used to really measure 2 inches by 4 inches. Over time, that has been shaved down, right? So we can have higher manufacturing capacity. We can grow the tree faster, because now all we need to do is get 1.5 inches in thickness by 3.5. So a 2x4 actually measures 1.5 inches by 3.5. And it's been that way for as long as I can remember. I know it was used in the late 40s, right after World War II. Might have even been used before that, but I think that was the first really big sequence where they were using dimensional lumber as opposed to rough sawn lumber. Rough sawn lumber would have been back in 1800s, you know, where we went from log construction to plank construction, and the lumber was whatever the tree gave you. So sometimes you had a piece of rough lumber, it'd have bark on the edges, and it would be that tall or wide. Sometimes it'd be this big if it came out of a big tree. But to get to the speed and consistency and more of a product, we went to dimensional lumber. As the dimension goes up, there is a change, and you need to be aware of that. So we go to a 2x6,
which is 1.5 inches by 5.5. But when we move from the 2x6 to our 2x8, all of a sudden we lose another 1/4 inch, typically thereabouts. It's an approximate, different mills give you different. But this one is about 7 3/16. We'll call it 7 1/4 for practical purposes and consistency and course material. So you have 1.5 inches by 7 1/4.
So 2x4, 1.5 inches by 3.5. 2x6, 1.5 inches by 5.5.
Then we step to the 7 1/4.
So with a
If it's
2x10,
it's 9 1/4.
okay.
Across the width of the board. The thickness is still going to be the 1.5 inches. If this were a 2x12, it'd be 1.5 inches thickness, and then it would be 11 1/4.
So why is it important to note the size of dimensional lumber? Well, it helps set our 16-inch on center. We need to know that this is 1.5 inches,
Exactly.
so we know what the halfway mark is, 3/4 of an inch. And it sets the thickness of our wall. So based on our specs, we might have a wall that's a 2x4 exterior wall. but we may need it to be a 2x6 because we need more insulation. The 2x6 is deeper if we're thinking about it in a wall setup, which makes a bigger cavity to put more insulation. Or we might need it to be a load-bearing wall, so they specifically call out that we build a 2x6 or a 2x8 wall. There's many different reasons, but we need to know that dimension. So when we lay that in the wall and we're thinking about our insulation, a lot of insulation is made based on the wall thickness. So if it's spec'd out as a 2x4 wall, we know that that's 3.5 inch deep on our wall cavity. A lot of batt insulation, this is just a fiberglass batt, B-A-T-T. It's 3.5 inches thick, and there's varying grades. So we know that that 3.5 inches thick is gonna fit right in our wall cavity, and everything's gonna line up and be properly spaced. If it was a 2x6 exterior wall, that batt insulation is now 5.5 inches thick, and it makes contact to the back of the wall sheathing and the face of our stud because we're trying to fill that entire cavity. So dimensional lumber, you need to know the sizing. If we're ordering board feet of lumber, we need to know how to calculate the board foot based on our width, here the width, and then the dimension across the face of the lumber. And it also helps us pre-build headers. So we just said 2x4 is 3.5 inches thick. So if I take my 3.5 inch studs and I lay them in the wall, I can actually have one of my crew off-site or off the platform building my window headers. We know the rough opening. We know how many trimmers we need. So all they have to do is take the rough opening plus the number of trimmers, and that gives them the length of their header. So they can start cutting the header components. But we've got a problem. We have a 3.5 inch thick wall, and here we've got two pieces of 2x6 put together. So if I've got 3.5 inch wall and I put my two dimensional lumber together to build my header, I'm at 3 inches thick. And that leaves a 1/2 inch gap, right? 3.5 inches deep on my cavity, but 3 inches of window header. Well, we can't leave that cavity because it's uninsulated, and structurally it's not going to support. If we run a piece of sheet goods over that and we have a 1/2 inch gap right here, the sheet good's going to collapse into the wall when they go to nail it or screw it. So do we have something on site that would be a 1/2 inch thick?
We've got all of our exterior sheeting typically.
So we can take a scrap of our exterior sheeting that was maybe 7/16 or 1/2 inch OSB and cut that scrap rather than throwing it away. We can cut that piece of scrap and we can sandwich it in between our header material, and we went from two pieces of dimensional lumber that were 3 inches wide to now we're 3.5 inches wide. That fills our whole cavity at the header height, and we've now built a proper wall. We're always have to be concerned with dimensions and lumber, floor systems. Everything comes back to understanding how to read a tape measure, understanding how the components go together, and where the weak spots are. So we work backwards for that. That's why we will constantly, you say, why do I need to know that a 2x8 is 7.25 inches? Well, if you're put in charge of doing the takeoff, counting the quantities of lumber that are in the wall, we need to know, especially if you're the one who's ordering the board footage, or if you're comparing notes. Wait a minute, the spec says that I'm using an R11 craft face batt. Well, once you know specifications and nomenclature, you know that that R11 craft face batt is 3.5 inches thick. Yeah. But what if the wall spec says it's a 2x6 exterior wall? You then, as the construction manager, know there's a problem in the specs. We've got a batt that is only filling up part of the wall cavity. So why? Was it a mistake? Is there something going on the outside of the wall that we don't know about? That allows you to have the conversation with the architect or the engineering firm to say, did we find a mistake, or is there something that I haven't seen yet?
Right. I think it's safe to say, always remember, unless that piece of material is standing by itself in space, materials are part of a system, and the system has to go together just so. And that's what us as managers are consistently doing, making sure that our processes are uniform. Yeah. And materials are designed to do that, just like the depth of a wall stud at 3.5 inches, a 2x4, and miraculously they've designed the insulation to fill that 3.5-inch void. And so it's our job to make sure that we're viewing materials as part of a system. You don't just slap it up on the wall, oh good, I did what I was supposed to. You've always got to have your mind in the game.
Yeah, and when one component in the system changes, you have to think about unintended consequences built into that system and where that may cause a problem. And that's where conscientious trades and construction managers are always thinking about who came before me. We always check the work that was done. Even if Scott and I have worked together for 30 years and he says, yep, layout's done on the sill plate, that doesn't stop me from pulling out my tape measure and just doing a quick check. It's not that I don't trust him. It's just we all know we're people. We could have misread the tape. We could have read the wrong line on the tape. So we check the work in front of us, and then we try to do our part of the job as good as possible so we pass on a good project to the next trade that's coming behind us.
Always measure twice and cut once.
Famous saying, but it's
true across all levels of management, guys, you know, and not just self-performing, but always check yourself before you make your final decision. You'll be thankful that you did, because you're going to minimize the amount of mistakes that you're capable of, because we're all capable of them.
kind of wish I'd gotten paid by the mistake
Oh,
early
my
in
Lord.
my career.
We wouldn't be here.